Today we're going to look at 10.4 and its applications of our differential equations we've been working with. And so we're going to write and solve differential equations to solve with population growth, radioactive decay, Newton's law of cooling and heating. You can also do this for investments as well and all sorts of things. So the first thing we want to look at is this differential equation. dy dx is equal to ky. So basically, this is called a law of natural growth or a law of natural decay, depending on whether k, this constant right here, is positive or equation. So if I separate and integrate, I'm going to get 1 over y dy is equal to k times dx. Now again, remember, k was a constant here. So I'm going to do the integral on both sides. I have ln of is equal to kx plus c. Remember, we only need one constant on those. And then if I'm going to isolate this, I can have e to the kx plus c. Fantastic. Okay. Sometimes we might just write y equals e to the kx plus c, because if we're going to be talking about a population, the people would be positive. We wouldn't have to worry about having negative people, unless we're thinking about zombies or something. So we would have something along these lines. Now, let's say I had an initial condition within this, like maybe y of 0 equal to, we'll call it y0. Like you do. So then if I was going to solve that, I would have y0 is equal to e to the k times 0 plus c. So really y0 is equal to e to the c. If I'm solving for that initial condition, then I'd have ln of y of 0 equal to c. You could have also solved this initial condition problem way up here, okay, and worked with that. I tend to do that actually, and I did that on a lot of the answer keys for the section. And from here, we get basically c is ln of y0. Well, going back to my equation, I have y equals e to the kx plus ln of y0. That doesn't look that friendly right now, and definitely doesn't look familiar at all. But I'm going to use some rules of exponents that might not be that familiar, and I'm going to do them kind of backwards. Remember when we would multiply and we add the exponents? Well, since these two pieces are being added, I can rewrite it as multiplying two separate things. Oh, that doesn't look that nice. Okay. And so I have e to the kx times e to the ln of y0. Well, why would I do that? Well, by my log laws, I can simplify this one right here. And what I would simplify that to is, because my bases are the same, it's just y0. Now, if I rewrite that, we get y equals y0 e to the kx. Now, that may or may not ring some bells. What if I wrote it as, instead of y0, what if I called it p for principal investment, maybe? E. Instead of calling it k randomly, what if I called it r for rate? It's still a constant. And then t for time. So what I've actually shown is the exact same equation as PERT that you probably memorized in Algebra 2. So, and that happens anytime that our dy dx is equal to ky. So, cool, huh? So how do we use that? Well, anytime I have dy dx is equal to ky, there's that initial value. We know that this is always going to come out as y equals y0 e to the kx. Okay? So we can do the same thing with p's. So if I have dp dt is equal to kp, usually if I'm doing this p is representing the population. Okay? If I wanted to show this growth, okay, that's going to be y is equal to, or rather p is equal to, sorry, P is equal to our initial population, E to the KT. And again, you can see that PERT coming in there as well. So the other thing we have here is the relative. So dP dt, this is called the growth rate. We also have the relative growth rate. The relative growth rate is 1 over P times P dt, which is really just what K is. Because if I isolate for P, if I isolate for K, sorry. Okay. Now, I've got one more of these like this, radioactive decay. Oh, radioactive decay, your book represents with dm dt is equal to km. But that looks exactly the same as the last two. It would just look like m of t is equal to m0 e to the kt. Notice in all of these, we just have our initial value here, e, and then that rate up at the top. So the half-life of kryptonite is 12 years. Lex Luthor has a sample with a mass of 100 grams. Write an equation for the amount that remains after t time. Now again, the decay here is going to be based off, we would have, it's kind of that, dm dt is equal to km, because it's a radioactive decay or a natural decay. K obviously will come out negative because that's what we're looking at. If I go and rearrange that, you end up with PERT. I'm going to just work with PERT because that's what we're more familiar with. I'm going to use this, actually I'll make it a K. So I'm going to use this to find out what that K value is. So it takes 12 years for half of it to be gone, so this will be 12. Okay? And then we'll have ln of 1/2 is equal to 12k, and k is equal to ln of 0.5 over 12. Okay. At this point, when you did the problem like this in Algebra 2, you probably would type that into your calculator and have it spit out an answer. Okay. Now I've got a is equal to 100. That's that initial value. Okay. And then e, the ln of 0.5 over 12 is t. I'm going to do a little math magic with my exponent rules here. Now, instead of adding here, I have ones that are multiplying. And actually, I'm going to do one other thing. I'll write this as ln of 0.5 and t over 12. Go with me. Multiplication is commutative and associative. I can rearrange that to my heart's content. Now, instead of adding in an exponential is like multiplying with the same base. When I raise powers to powers, I'm multiplying that exponent spot. So this is that multiplying. You have e to the ln of 0.5 to the t over 12. My base is matched again. So I can actually simplify this to just 1/2 there, to the 12. At this point, you might recognize this as the half-life formula that you may again have memorized in Algebra 2 or even in chemistry. But that's basically our equation. It's 100 T over 12. And when will it be reduced to 30 grams? Well, that's what, oops, sorry. When will it be reduced to 30 grams? We would make a 30, and we want to solve for T. Yep, 3, 5, 12. I'm going to convert to a log. You could log both sides or ln both sides as well. Our calculators are so fancy now that you could have this. And so here's an exact answer, and a decimal approximation would be about 20.843. We're looking at units. This was years, so it'll take about 20 years. Almost. Okay. All right. Next one. Keeping it cool. Newton's law of cooling. Newton's law of cooling is dt dt, which of course we have two different t's. We actually have three different t's here. We have capital T, lowercase t, and ts. Now this is the temperature. Okay, this is the surrounding temperature, which happens to be a constant. Okay, and this is our time. And again, K is going to be a constant. If we're cooling, K is going to actually be a negative constant because it's going to be decaying things. So what we're going to do now is I am going to separate and integrate because this is another separable differential equation. So separate dt equals to k. So I separated. Now I'm integrating. All right, I'll have ln of t ts equal to k plus c. I can convert to an exponential. Actually, well, I'm also going to use that t of 0 is t0. So I'm going to show how you can find that value before I convert. So I would have ln of t0 plus is equal to 0t plus c, which is a nice thing because look at how nice that is. I don't have much to solve that. My c is equal to that. That's just lovely. So now I'm going to convert to an exponential. So I'm going to work off of this line for a minute. Bring it back down. Okay, now I found my c. So if I convert to an exponential, my base is e. So t minus ts equal to e to the kt plus c. Oh, but wait, I know what my c is. I need to leave that. We're going to e to the kt plus ln of t0 minus ts. Okay. And I can separate that using my exponent rules, which means that that's really just a coefficient. So I'd have, so long as my initial temperature is hotter than my surrounding temperature, that will come out positive. So since we're going to focus on it as cooling will be like that, you can agree that if I was doing it the other direction, I would just swap them. And one more step. T is equal to our initial temperature minus the surrounding temperature, e to some constant k times t plus the surrounding temperature. Newton's law of cooling, which should look familiar from either pre-calculus or algebra 2. But when you saw them in pre-calculus or algebra 2, it was just, hey, here's a big messy formula, memorize it. Whereas here now you can see where that formula came from. It came from this differential equation. And it's that the temperature is equal to the proportion of the difference of this current temperature and the surrounding temperature. So Miss Marhefke brews a cup of tea at 180 degrees Fahrenheit and places it on her desk in her 72 degree Fahrenheit classroom. After 5 minutes, her tea is now 171 degrees Fahrenheit. After how long before it is the ideal temperature of 162 degrees Fahrenheit? So I have my surrounding temperature is 72 degrees, and I also have an initial temperature, and I have T at 5 is equal to 171. So I'm going to use that to help me find my K value, because you can see the difference here is I don't have what K is. So I'm going to go with 171 is equal to 180 minus 72 for that surrounding temperature, the temperature of my room, e to the 5k. I'm doing mine within minutes. Depending on the problem, you might do it within hours, or it doesn't really need parentheses on that, or you might be doing it. It would just depend on the context. So just going through. And I got 11 12s here. 12 over, don't know. Oh, I started right there. Equals k. So, which if I wrote the decimal, you're going to have about negative 0.0174-ish. Okay. Then the next part, because I'm not done yet, my goal is to find out when would it be that ideal temperature, because that's really more important to me. And so T is equal to that 108. And then I could write this as negative 0.0174 T and then plus 72. Or I could do a little math magic on this and have it ln plus T. Depends on your comfort level with these exponential properties, and also what the numbers are. So, and also if you have access to a calculator on a problem, or where you're supposed to round to, all of those can affect whether I do it this way. So then I want to know when it's 162. And I'm going to solve for T. And I'm going to use, since I converted it this way, I'm going to use a log base. If I had used the decimal instead, I'd probably use ln instead. So T comes out as about 10.47 minutes. So depending on the question, it's 10.476 minutes after it was originally brewed, or within another 5.476 minutes from the last. So this concludes lesson 10.4.